Hello folks, we're back with another topic in multivariable calculus. Today we're going to do directional derivatives and gradients. We're going to see the relationship between directional derivatives and gradients. Now, because we're talking about at these three dimensions when we say multivariable calculus, it's kind of hard to imagine what's going on. And these surfaces live in three-dimensional space. My drawing capabilities are very limited, so I thought we could see this using this piece of fruit. So I got a kiwi, and we're going to talk about directional derivatives using kiwi. I'm going to label a point on this kiwi. Let's say we have this point on the kiwi, okay? So I labeled it right there. You can see it. Now the question is, can we talk about tangent line? Okay, now remember, in good old single variable calculus, it was kind of easy. If you had a curve like this and a point on that curve, you can always talk about the tangent line. Okay, drawing it was really easy because there was only one tangent line when the curve was differentiable. Now, even if you have a very smooth, okay, very nice three-dimensional object like this kiwi, you would hope that it's differentiable. Defining a tangent line is not going to be possible because there is no unique way to do it, right? Am I going to define it this way? Am I going to go this way? Okay, so there's a lot of, take your pen around, and there's a lot of different directions you can define the tangent line to be, right? Okay, so that's the difficulty we face when you're talking about three-dimensional objects, multi-dimensional objects. It's not possible to define a tangent line without giving a direction. So what do I mean by giving a direction? Remember, if we have a vector v, okay, and v is equal to v1i plus v2j, right? This didn't make much sense in terms of direction. You think of this as a line segment. It's got some direction, but anything on that line has the same direction. So when we say direction, we were talking about the unit direction, right? The unit direction, the unit vector in the direction of v. So how did we find this unit vector u? What we did was we would divide v by its length, okay? So all the directions here are going to be unit. Let's say this is the paper is the xy plane, okay? The paper is the xy plane, and we have the z line coming towards you. So I labeled this point. You first have to tell me, okay, which way you want to take the derivative. Okay, you got to tell me a direction. So let's say we labeled this direction on the paper. Now I'm going to put it back here. So what I need to do is I'm going to bring myself, okay, so that direction was hard. Let's try this direction. This is going to be easier for me. Okay, so this direction, we want to cut it this direction. So I'm going to bring my knife and cut this kiwi. Okay, so in that direction, vertically, I'm going to cut it right down the center. Okay, so now on that point, so the point is gone. Sorry, yeah, it was right here. It was right here. Okay. So it was right here. The point was right here. So what I need to do is let me label this side also. Okay. So what I need to do is now I need to talk about the tangent line to this curve. Now note there's a very nice curve. This is a curve, right? This is a two-dimensional curve. So we can talk about the tangent line in this direction. So I can just find now the tangent line in this direction now is unique. In the direction of the vector is unique. You see? Okay. So so let's go again. You gave me a direction. You gave me this direction. You gave me a point. I cut it vertically parallel to that direction, just like that. You can see the arrow still. And then I'm going to take, once I do that, I just have a two-dimensional curve, so I can calculate the tangent line. All right, so that's what we're going to do basically. So hopefully we'll eat the kiwi after class. But now let's get down to math. All right. So remember the derivative formula, okay? When we had dy dx, okay? Dy dx formula, okay? Where y is equal to f of x, some function, let's say, okay? Then we're going to define dy dx, or in other words, we could write it as f prime of x, right? Was very simple when you had a two-dimensional curve. That was limit as h goes to 0 f of x plus h minus f of x all over h. Okay, so this was true when you had the two-dimensional curve, something like this. We can plug in points later on, and we wanted to calculate the tangent line, something like that. Okay, so given a vector v, okay, given a unit vector, let's call it u because it's unit, u, okay, and let's say it's got components u1 I plus u2j, sorry, u2j, okay, it's got components u1i, u2j. We want to find and a function, multivariable function, a func, okay, z equals f of xy. It's in terms of xy. We'll do an example in a second, okay? So how would we define the derivative? Now, what I think we should do is, well, we cut our kiwi, we have to define this. So think about, we cut the kiwi, this is the point, and then this is the line, right? Okay, so we have to define this line. So how can I define this guy? Well, I can parameterize it using u, okay, the unit vector u. So I can say this is going to, if this point is x naught, y naught, okay, let's call it point p naught is x naught, y naught. Well, one thing I can do, right, is I can parameterize it as x naught plus the first component, u1, right, u1 times, let's say, s, okay? And x and the y component of the line would be y naught plus u2s. Now, you might have seen this before. We usually use t instead of s, okay, because we think about the parameterization as being in terms of time, okay. Here, we're not going to use t, we're just going to use s, so you just, again, plug in values to s1, 2, minus 3, minus 5, and that's going to give you points on the line, the xy coordinates of the points on the line. Why do we use s? Because we think about it, now we have a vector, we want to find, you know, we're going to do that f of x plus h minus x. The h here is just going to be the arc length component, okay? So it's going to be the arc length component of the vector in that direction. That's why, because whenever you say arc length, you know, you think about the variable s. That's why we're using s. Okay, so that's a lot of talking. Now, we have parameterized this. So what is something I can do to write down the derivative? Okay, so we're going to do a big D, okay, in the direction of the vector u, okay, you don't have to put the arrow if you don't want to, of f, okay, is going to be, okay, limit as s goes to 0. S is like my h here, it's going to go to 0. In the old days, I had f of x plus h. Now I have to have f of x plus, well, h was move h units right. Now you're going to move u1 plus s units right? Okay? So s times u1 units, comma, y plus s times u2 units, okay, minus f of xy all over s, okay, whatever s is, okay. So if this limit exists, okay, so if this limit exists, we say the function is basically going to have that directional derivative. So the directional derivative at point, directional derivative at p naught, okay, p naught would be, I would just evaluate this at p naught. I would just write du f, okay, evaluate that p naught, okay, is basically this one. Now, instead of at the end, you're going to get a formula in x's and y's, you just plug in the point p naught. And if the limit exists, it might not exist, remember. If the limit exists, the function is going to have that directional the directional derivative is going to exist. If it doesn't, it doesn't, basically. It doesn't exist. Okay, so this is the directional derivative of f in the direction of the unit vector u. This is very important. If you're not given a unit vector, you must divide it by its length at the point, sorry about that, at the point p naught. What was p naught? P naught was x naught, y naught. Okay, so that's a lot of variables and theory going on at the same time. I think it's time for an example to see how this works. Now, be warned here, I'm going to do the same function and I'm going to do two different directional derivatives. So it's going to look like we're doing the same stuff twice. We are not. It has a very big point that I'm trying to make, which I'm going to come to in a second. So bear with me. Hopefully this is going to lead somewhere nice. So let's take a very simple function. Let's say we have f of x is equal to x squared y. Okay? So we have this, whatever it looks like, we don't care right now. Okay? We have this three-dimensional function, and somebody asked me, okay, to find the directional derivative. Find the directional derivative, okay, in the direction of v equals 2I plus 0j. So it's basically just has an x component, okay? It doesn't have a y component. Now, the first thing I wanted to say is, of course, they're trying to fool us or something like that, because v is not a unit vector, right? We need to find, okay, it's not a direction, it's got some length. A direction, remember, it's a vector of length 1, okay? Basically determines the direction, so we need to find u, okay? So what we're gonna do is, we're gonna find the unit vector. Okay, so then u is gonna be equal to v over length of v. Okay, now of course v is 2I plus 0j. I'm gonna drop the 0j in a second. Okay, and what's the length of it? Remember, well, it's gonna have length 2, isn't it? So it's just gonna be 2 squared plus 0 squared in the square root. Okay, we're gonna get now, that's gonna be 4, so we're just gonna get it's I plus 0, 1I plus 0j. Okay, so if we're talking about directional derivative, the directional derivative of u in the direction, so this is a u. If we're talking about the directional derivative of f in the direction of u, let's plug it in. We need to do limit as s goes to 0. Okay, so notice that if I parameterize the line now, okay, if I parameterize the line is just going to be x naught plus just 1s, right? 1 times s. Okay, it's just x, and y is just equal to y naught plus 0s. There is no component. Okay, so this is just x naught plus s, right? Okay, so instead of wherever I see an x, okay, I need to do x plus s, and that's what we're gonna do. If we're thinking about, we're plugging the point x plus s. Okay, so we're gonna do f of x plus s y minus f of x comma y, sorry, all over, we're going to do the length s, okay? All right, so for our particular function, remember our function is x squared y, so let's just plug it into it, okay? So don't forget your limits. We get limit as s goes to 0, f of x plus s, so that's going to be x plus s, the whole thing squared, times y, all right, minus x squared y all over what we got here is just going to be s. Okay, now we can factor out the y's, right? We can factor out the y's. So if we do that, I think we're going to get something nice. So let's just get rid of the y's. So y times, open a big parentheses. Now I'm going to start opening this up. That's x squared plus 2xs plus s squared, okay? Minus, we factor out the y, we have an x squared here, right? All over s. Now the nice thing here is obviously the x squares are going to cancel, okay? And now, when I do the cancellation by s, okay, when I do the division by s, what do we have? We have limit as s goes to 0, y times, when I cancel the s, I'm going to get 2x and I'm going to get plus s, okay? As s goes to 0, obviously this is going to 0, so we actually just have 2xy, okay? So we have 2xy. So if we take, if we wanted to, this gives you a general formula for the directional derivative in the direction of that vector. If we wanted to say, let p naught, let's just pick any old point. I don't know. Let's pick 1, 3 or something like that. Okay, 1, 3. Okay. Then du if, okay, du of this u is on the bottom, it's a subscript, evaluated at p naught, okay, p naught is the point 1, 3, would just be 2 times 1 times 3, which is 6, right? Okay. All right. Now, why did we do this example? So it was kind of like a cheap example, right? Because our derivative was just had an x component. It didn't have a y component. This is not the sort of example you would see in general. The reason I did this is just so that you could see it with your own eyes. If we're talking about the derivative in the unit vector, derivative in the direction of the unit vector, which is just in the direction of the x-axis, that's really the same thing as taking the derivative of f with just respect to x, isn't it? So this should be, just from our knowledge, this should be f of x. Okay, f sub x, derivative of f with respect to x. And now we can see that, right? If you take the derivative of f with respect to x, in other words, if you do df dx, right? df dx, what do you get? You get just 2xy because y behaves like a constant. Okay, so it was just a ton of work to get the same answer, but at least the formula makes sense. We do it this way, we get the answer that we know. Now let's go on and pick a fight with a different function. Let's take a different vector, a real vector this time. Some vector that's gonna be different. It's gonna have both x and y components. So I think we should be doing, okay, we should do something like this. Of course, I picked the numbers easy again. So as an example, let's do f of xy. F of xy is, again, same function, x squared y. We want directional derivative. Okay, in the direction of v equals 3i plus 4j. Okay, again, I'm trying to fool you, right? This is not a unit vector. Okay, so direction is just the unit vector. We first need to find the unit vector. Okay, so then u is going to be equal to v over the length of v. Okay, so v is our good old v. We have 3i plus 4j, the good old guy. Okay, all over, well, I picked the numbers again, nice, 3 squared plus 4 squared in the square root, so that's going to be just 5. So we have 3/5 I plus 4/5 j. Okay, so if we were to parameterize the line, right, then we would get x, we would want to do something x plus 3/5 s, the x component, and y naught, okay, plus plus 4/5 j. Okay, so instead of wherever I see an x, I'm just gonna plug in this x plus 3/5s. Okay, so let's write down our formula. The more we write it down, the better it's gonna be for us to memorize it. It's gonna be much easier. So when I'm talking about df in the direction of u, directional derivative of u, what is that gonna be? That's gonna be limit as s goes to 0. Okay, we have f of x plus u1s, right? And y plus u2s minus f of xy, all right, all over, we got s. Okay, so let's plug this in. Okay, let's just plug this in. For our function, remember the function is, you can just see it right here. The function is x squared y, so I'm just going to plug it into there. We're going to get limit as s goes to 0, okay? F of, well, u1 is just 3/5, right? So we have f of x plus 3/5 s, the whole thing squared, right? Times y plus this y component was 4/5 s, okay? Minus, well, x squared y, okay? All over s, okay? So, all right, I mean, right, there's a saying that a good mathematician is a lazy mathematician. I look at this and I'm like, all right, I really don't want to calculate this. Some engineer could do it. So I'm gonna think of a smart way. Let's do some work, and maybe we'll see something smart. Not to open it all up. It's gonna take forever. All right, so let me just open this guy up. That's gonna be x squared, right? And plus I'm gonna have 6/5 s. Okay, xs. It's gonna be twice this. All right, s times x. Plus I have an s squared. That's just the first guy opened up. And then plus 4/5 s, okay, minus x squared y all over s, okay? Now, it was supposed to be better. It's just becoming much worse. But have no fear, because your friendly neighborhood mathematician is here. We're going to just notice something, okay? Every term that has something more than s in it, right, is at the end going to go to 0, because only the terms with s are going to cancel out. The terms with s squared and s cubed will still have an s at the end of the day, and when you plug in s equals 0, they're going to be 0 anyways. So I really need to calculate only the terms up to having a multiple of s, okay? So that's not hard. Let's just keep it here. The last step, let's just keep it here before we move on to the next page, okay? So what I can do now is I'm going to start multiplying this. Well, when I multiply the x squared and y term, I'm going to have an x squared y term, right? Okay. Then how can I get an x? Well, how can I get an s term? Well, I can multiply this guy and this guy, right? So that's going to be plus 4/5 x squared s. Okay. Now, let's come to this term. When I multiply with y, I'll get a s term in it also. So plus 6/5. We're going to have xys, right? Xys from this guy and this guy. Now, I'm not going to do the multiplication of this guy y, because that's going to be an s squared. It's going to go to 0 anyways. Similarly, all the terms including this. So plus some junk. I don't care what it is. Okay. They all have more than s in it. Minus x squared y all over, sorry about that, all over s. Now, the nice thing here is, of course, these guys cancel out, and I only have these terms plus some s squared terms plus some s cubed terms, so the only guys that are going to survive are going to be this. So once I cancel out the s, what is it going to be? It's going to be 4/5 x squared plus 6/5, okay, x times y. Now, you might think, okay, oh my goodness, this was really, really boring. I share the same opinion. Okay, I'm of the same opinion. This was really, really boring. It's nice that you can do it if you like this sort of thing. I'm not terribly hot on it. So I'm thinking, is there a simpler way to do this? Okay, I'm thinking, is there a simpler way to do this? And it turns out that yes, there is. We're going to give a proof of it, just 2-line proof of it in a second. Now, I want to ask you the following question. For the same function, calculate f sub x and f sub y, the partials f sub x and f sub y. For the same function, what was the function? Remember, we were talking about the function f of xy was x squared y. Okay, this was our function. Now, this is easy. We already learned this. And what was it? So I'm just going to treat y as a constant now. So this is just going to be 2xy. Okay, and f of y. Now I'm going to treat x squared as a constant. So it's constant times y. The derivative of y is just 1. So it's just going to be x squared, right? Okay. Okay. Now remember the directional vector that we worked with. Remember, okay. U was what? It was 3/5 I plus 4/5 J. All right. I think something nice is about to happen. Let's move this out of the way. Okay. Something nice is about to happen. And we found DUF, okay, as 4/5 x squared plus 6/5 xy, didn't we? Okay. Now, I'm just going to ask you this. I think this is going to be equal to 2xy I. Okay, I'm just taking the fx. This is f sub x. Okay. Plus, I'm going to take x squared j. This is just f sub y. Hold on, what is he doing? Well, I'm doing something nice. So I'm going to take this and I'm going to multiply it by 3/5 I plus 4/5 j. By multiplication, I mean the dot product. Sorry, you didn't see that. Okay, so I'm taking our unit vector. I'm just making, this is going to be called the gradient later on in a few minutes. So I just took the partials, the f sub x, f sub y, created the vector out of them, and I'm doing it dot product. And I think it really is, so first coordinate times first coordinate, you do get 6/5 xy, right? Plus second coordinate times second coordinate, you get 4/5 x squared. Okay? And that's exactly the answer we found. So this is really weird. I mean, this shouldn't be happening by chance. I just picked out this problem out of the blue. Just try to make the numbers easy. But it really works in general. So this is going to be our formula. Okay? We're going to say DUF, I'm going to prove this in a second. DUF is going to be, what we're going to say, it's going to be f sub x, okay, I'm going to write this in vector notation, f sub y as a vector. Remember, this meant f sub xi plus f sub yj, dot product, u1, u2. Okay? It's just that. So this is much nicer and much faster than calculating the derivative by hand from the definition. Okay, so it's just like single variable calculus. We're developing a rule. That lets us calculate these derivatives much faster than trying to do the limit definition. Okay, so all right, so why is this happening? Okay, why did this happen? That's something we should be thinking of, and that's what I'd like to do next. Okay, so one way I'm gonna write another definition. Okay, so sometimes in different books you see that duf, okay, duf, the function f, evaluated at the point p naught. Well, some books like to write like this. They say df ds, okay, where s is the arc length component, okay, of the unit vector. Df ds, okay, times, okay, so u comma p naught. This is a subscript, big P naught, okay? This is the direction, unit vector. Oh, that's horrible. Sorry. And this is a point, P naught, X naught, Y naught. Okay, so it calculates the direction of, it calculates the derivative, the slope of the tangent line, I guess, okay, in the direction of the unit vector u at the point P naught on the surface of F. Okay, so these are the same thing. The reason that they say ds is, remember, we parameterized it using, we parameterized the line using s. We said x naught plus u1 times s. So instead of t, we used s. And that makes sense because we're talking about arc lengths and you want to use s instead of t, really. So these are just the same thing, but this notation is a lot more helpful. So what we're going to do now is we're going to try to prove this gradient formula. We're going to try to prove this gradient formula. So let's try to write down some math. This might be boring for you guys. This is some of you guys, but it's nice to see the proof. It's very simple. So given a parameterization, what's going to be our parameterization? X equals x naught plus u1 s, y equals y naught plus u2s, okay, of the line through the point P naught, and let's give it coordinates x naught, y naught. All right. Parameterized with the arc length parameter s, okay, is in the direction of the unit vector So it's got to be always unit. U equals u1i plus u2j. Okay. Using chain rule, we'll use the chain rule. Using chain rule, we get the following. Okay, so I'm gonna just leave it up here so you can write it down if you'd like to. Let me just go over the setup again. We have some sort of surface on some function f, right? Defined by some function f, and we pick a point on it, p naught, okay, and we want to find the directional derivative. So somebody gave us this vector, okay, and we parameterize the line going through this point in the direction of this vector. So how do I do it? Simple, just like that, okay. And now we're cutting it vertically. Now we're going to get a curve. We want to define the derivative, okay. We already defined it. We want to find a nicer way to do this. So what I'm going to do is, well, what was that? What was the definition of that? The definition of that was, so we were talking about du of f evaluated p naught. But now let me just write it using the other symbols, the other notation that we learned about, which is going to be df ds. Okay, this is the same thing as df ds, the arc length parameter. And the vector is u, and the point is p naught. Okay. Now, well, we can use the chain rule. Here is where the chain rule comes in. Well, if I want to find the df ds, what can I do? I can take the partials df dx, go from, okay, so we have, let's draw our thing here. Well, f was in terms of x and y, right? But now I'm writing both x and y in terms of s. Okay? So I can go and say that this is just going to be df dx evaluated at p naught times dx ds, whatever that is, plus df dy, right? Just the chain rule that we saw last time, evaluated at p naught, times dy ds. Okay. So did it really make everything easier? Well, I think it did, and the reason is because this is the arc length. Sorry, you're not seeing that. Because this is the arc length parameterization, we use the arc length parameterization of the line. The x ds, that's just the x component of the vector. This guy is just u1. Similarly, this is just the y component of the vector, of the unit vector. So that's just u2. Okay, so this simplifies down to df dx evaluated at p naught, okay, times just u1 plus df dy evaluated at p naught times just u2. All right, so not too bad. Now I think I can write this as a nicer step, okay? As a nicer step, we can write this as just df dx. So it does show you the relationship. Evaluated p naught. Let me write it as a vector, and df dy. So it's df dx evaluated p naught I actually. Df dy evaluated p naught j. So let me use this notation. Times, remember this meant the vector I plus j, times, it's just the vector u1, u2, or in other words, it's just our guy, okay? So, all right, so this is nice. We're going to give this guy the name, so we're going to say, we're going to define definition. We're going to say gradient of f, del f, is equal to f sub x, okay, f sub x, not fx, f sub x, I, plus f sub y, j. Or in other words, it's just this guy, f sub x, f sub y, okay? This is just the gradient, funky term, gradient of f, okay, del f is f sub xi, f sub j. So then, from here, I can just write this very nicely. I can just say, well, this directional derivative at u, f, at the point p naught, well, I can calculate that very easily. I can say this is the gradient of f evaluated at p naught, okay, times the vector u. Now, these are both vectors. This is the dot product. These are both vectors. So these are vectors. Let me just show that they are vectors. I'm going to drop the arrows later on. But this is a nice little formula. Okay? So the chain rule, last time, the chain rule that we saw, okay, it just seemed like it just seemed like a generalization of the chain rule for single variables, which it certainly is. But I remember in the last lecture, I commented that it was going to be very useful later on. So it stops us, it stops, it doesn't stop us. So we don't have to do the directional derivative from the definition of the limit, okay? So we can just do this multiplication dot product of two vectors. It becomes very, very easy now. And then it's going to let us do some other things, which is going to be for another lecture. I'll see you soon, hopefully. Later. Bye-bye.